In this video, we're going to talk about trig substitutions. Now, trig substitutions are an integration technique that will allow us to evaluate integrals that contain expressions like one of these three forms here. So the integral will have something like the square root of a squared minus x squared, or the square root of x squared minus a squared, or the square root of x squared plus a squared. Okay, where a is just some constant. So, for example, integrals like these ones. Okay, now notice all these integrals contain one of these three types of forms. So for example, in this first integral, we have the square root of x squared minus 4. So that's of this form. Notice the a in that case would be 2, right? Because 4 is 2 squared. This integral has a square root of 25 minus x squared. That's of this form, okay? Where the a is 5. We have one down here, the square root of x squared plus 1. That's of this form here. In that case, the a would be 1. So all these integrals contain something like one of these top ones. Now, this one down here, we have 4 minus x squared to the 3 halves. You might think, okay, that's an exception. But actually, we could think of 4 minus x squared to the 3 halves as being the square root of 4 minus x squared cubed. Okay, it's like 4 minus x squared to the 1/2 power, then raised to the 3rd power. So all these integrals are integrals that we can do using what are called trig substitutions. Now notice none of these integrals do we see any sines or cosines or tangents anywhere, but we're actually going to use trigonometry to help us solve these integrals. Okay, so how do we do this? Okay, so what does trig substitution involve? Well, the idea is this. We're going to make a substitution to simplify this square root. Essentially, we're going to get rid of the square root. So in the case where we have the square root of a squared minus x squared, the substitution that we're going to make is x equals a sine theta. Okay, if we let x be a sine theta, this is going to simplify nicely, and in fact the square root will go away. Because notice what we have. We have the square root of a squared minus x squared, but if x is a sine theta, we have the square root of a squared minus, well, a sine theta squared is the same thing as a squared sine squared theta. Okay, but then notice we have two terms here. We have something minus something, and both of them have an a squared in them, so we can factor out the a squared. We have the square root of a squared times the quantity 1 minus sine squared. Well, remember that the square root of a product is equal to the product of the square root, so we can take the square root of this times the square root of this. But remember, 1 minus sine squared is cosine squared. So notice the square root of a squared is just a. Remember, the a was a positive constant, so we don't really need to put an absolute value of a there. And then the square root of cosine squared is just cosine. Okay, you can do a similar thing. So by the way, notice that the square root here simplified. When we did the substitution x equals a sine theta, this square root simplified to be a cosine theta. Okay, now if we're in the case where we have the square root of x squared minus a squared, the substitution that we're going to make to simplify things is x equals a secant theta. Okay, so this square root of x squared minus a squared, we let the x be a secant theta, and we work things down like we did before. It turns out in this case we have to use the trig identity that secant squared minus 1 is tangent squared. Okay, but when we do this and we break it apart, we end up getting a tangent theta at the end. Okay, so we make this substitution x equals a secant theta into this, we get a tangent theta. And you can do the same thing where we have the plus here, the square root of x squared plus a squared, which by the way is the same thing as the square root of a squared plus x squared. But if you do the substitution x equals a tangent theta and work things out, again, you'll need to use the trig identity that tangent squared plus 1 is secant squared. But if you work this out, it ends up being a secant theta. Okay, now this probably seems all confusing when you see this, and you might wonder, what does this have to do with integrals? But let me just kind of summarize what we just did. We have these three different types of expressions that we're going to have somewhere in our integral. If you have the square root of a squared minus x squared, the substitution you're going to make is x equals a sine theta. And when you do that substitution, when you do plug it in, it simplifies to be a cosine theta. Okay, when you have a plus, okay, the substitution you'll make is x equals a tangent theta, and it simplifies to be a secant theta. Okay, this expression here, once you make that substitution, simplifies to a secant theta. And then when we have the x squared minus a squared, well, the substitution is x equals a secant theta, and it simplifies to be a tangent. So notice when we do the substitution a tangent, it simplifies to a secant. When we do a secant, it simplifies to a tangent. So the tangent and secant kind of flip. Okay, so how does this help us? Okay, what do we do? Again, it probably seems confusing up to this point, but how do we actually do this integral? So let's do an example. The integral of 1 over x squared times the square root of x squared minus 4 dx. Okay, now notice we have an x squared minus 4. So it's like an x squared minus a squared. Now the a would be 2. Okay, the a is not going to be 4. The a will be 2 because it's x squared minus 4. So our substitution is going to be x equals 2 secant theta. Okay, so let's do this substitution. X equals 2 secant theta. Well, if x is 2 secant theta, what's dx? What's the derivative of that? Well, remember the derivative of secant is secant times tangent. So the derivative of 2 secant theta is going to be 2 secant theta tangent theta d theta. Okay, so what we're going to do now is just substitute everything in. This dx is not going to turn into a d theta. It's going to turn into a 2 secant theta tangent theta d theta. That's what dx is. So don't just change dx to d theta. It becomes this whole thing here. Okay, now we still have 1 over the x squared. So plug in what the x is. That's this. And then times the square root of x squared minus 4, where the x, again, is 2 secant theta. Now, I've already told you what this square root will simplify to be, so you can kind of skip a couple steps. In fact, you can skip all the way on down to here once you get good at this. This thing is going to simplify to be 2 tangent theta, right, according to this right here. When you do the substitution a secant theta, right, like 2 secant theta, it'll simplify to be a tangent theta, or 2 tangent theta in this example. Okay, but I've decided to kind of write out all the steps, though. If you work this out, 2 secant theta quantity squared would be 4 secant squared theta. This inside here is also 4 secant squared theta minus 4, but then you can factor out the 4 right there. Then you can take the square root of 4 times the square root of this, but secant squared minus 1, again, is tangent squared. And so notice what we get is that 4, the square root of 4 becomes a 2, the square root of tangent squared becomes tangent. So again, once you get good at these, you can kind of skip all the way on down from this line up here all the way on down to here, because this square root just simplified to be 2 tangent theta, like I said it was going to. Okay, now we still have this out here and this down here, but notice the 2 and the 2 will divide out, and same thing with the tangent and the tangent. And this secant will divide out with one of these secants, right? This is a secant squared. So what we're left with in the denominator is a 4 and a secant theta. So let's bring the 4 out front. So it comes out as a 1/4. And we have the integral of 1 over secant theta d theta. Now, how do we integrate 1 over secant theta d theta? Well, remember, 1 over secant is the same thing as cosine. Okay, and the integral of cosine is easy, right? It's just positive sine, right? Remember, the derivative of cosine is negative sine, but the integral of cosine is positive sine. So we get 1/4 sine theta plus c. Now, that's not our final answer, because our final answer should have x's, right? Because our original integral had x's. So how do we where do we go from here? We have 1/4 sine theta. Well, what's sine theta? Well, remember, the x is equal to 2 secant theta. Another way of writing that is that secant theta is x over 2. Right? Divide both sides by 2. Secant theta is x over 2. So if we were to draw a triangle here with a theta, a right triangle with a theta, secant theta, remember, is hypotenuse over adjacent. Right? It's the flip of cosine, which is adjacent over hypotenuse. So secant theta is x over 2. So we put an x here and a 2 here. And then by the Pythagorean theorem, the other leg of the triangle is going to be the square root of x squared minus 2 squared. Right, the square root of x squared minus 4. Okay, so if secant theta is x over 2, notice that cosine of theta would be 2 over x. Well, what would be sine of theta? Well, it's opposite over hypotenuse, right? Sine of theta would be the square root of x squared minus 4 over x. Okay, so that's what sine of theta is. So that's the idea. If secant theta is x over 2, you can draw this triangle and see that sine of theta would be this. Okay, so that's what we're going to plug in for sine theta, and that's our final answer. Okay, I've simplified it right here. This is our final answer. And you can check your answer. By the way, one thing that's really interesting to notice is the original integral looked like it had nothing to do with trigonometry. There's no sines or cosines or tangents. Same thing with the final answer. Okay, but we used trigonometry all along the way to solve this integral. So trig substitutions are integrals where a lot of times the original integral looks like it has nothing to do with trigonometry, and often the final answer will look that same way, but you're using trigonometry. You're using this trig substitution to do it. Now, how could we actually check our answer? Well, you could take the derivative of this. Okay, if you take the derivative of this, you'd have to use the quotient rule and the chain rule and so forth. But if you do that and you simplify it down, you should get this original integrand. Okay, try it. The derivative is a little bit messy, a little tricky, but it works out. So again, it's kind of an amazing technique that this actually works. Okay, so I want to mention a couple things about this. You might wonder, how is a trig substitution different than a u-substitution? Well, the method is very similar to a u-substitution, except that it's backwards in a certain sense. With a u-substitution, you let u equal something that involves x. So, for example, you let u be 7x squared or something. But with a trig substitution, you let x equal something that involves u. Only we call it theta instead of u. Okay, so again, with a u substitution, you let u equal something that involves x. But with a trig substitution, you let x equal something that involves u. Only we call it theta instead of u, right? So notice we didn't say u equals something here. U equals something that involves x. We said x equals something that involves u. Only, again, we're calling it theta. Okay, and instead of finding the du, we find the dx. Okay, but again, it's similar in the sense that it's a substitution. And again, the second thing I wanted to mention, I've already mentioned this, is that with a trig substitution, usually the integral looks like it has nothing to do with trig. And same thing with a final answer. That's often the case as well with a final answer, but we use trigonometry to solve it. Okay, let's do another example. Now notice this one, we again have a square root of x squared minus a squared. So we're going to use a secant again for our substitution. If this had been 9 minus x squared, we would use a sine. And if this had been a plus here, we'd use a tangent. But those three ones are the only ones you're going to use. Sine, secant, and tangent. Okay, so we have x equals 3 secant theta. That's going to be the trig substitution. So dx will be 3 secant theta tangent theta d theta. Again, remember the derivative of secant is secant times tangent. Okay, and so what we get when we plug things in, so we plug in 3 secant theta for x here, right there. And then the dx, remember the dx, don't just change it to du. dx is 3 secant theta tangent theta d theta. Okay, now I have kind of skipped the steps this time. Remember this square root here is just going to simplify to be 3 tangent theta. Right, when you do a 3 secant substitution, it's going to simplify to be 3 tangent. So I skipped a few steps in this one. Okay, well now notice the tangent and the tangent will go away, and the 3 will go away, and now we just have the integral of secant theta. Well, how do we integrate secant theta? Well, remember there was a special trick that we did from the last section. In fact, that was part of the reason that we did those trig integrals in the last section, is that now when we're doing trig substitution, we end up getting some integrals that involve trig functions. And it turned out that the integral of secant was natural log of the absolute value of secant theta plus tangent theta, okay, plus c. And remember, there was kind of a trick. Basically, it was kind of a clever trick you had to do. You had to multiply secant by a special way of writing 1. That way of writing 1 was secant theta plus tangent theta all over itself. Okay, but anyways, we did this integral last time, the integral of secant theta, and we came up with this. Okay, and so now the question is, what is secant theta and what is tangent theta? Well, notice we can rewrite x equals 3 secant theta as secant theta equals x over 3. And so, by the way, that tells us what secant theta is here. That's x over 3. Okay, the question is, though, what's tangent of theta? Well, we're going to have to draw a triangle. So all these trig substitution problems are going to involve drawing a triangle. If secant theta is x over 3, if this is our triangle with theta here, secant is hypotenuse over adjacent, so this should be x and 3. By the Pythagorean theorem, we'll have the square root of x squared minus 9. By the way, what you get here is usually what you have right in the integrand, so it should be in the correct order with x squared minus 9, not 9 minus x squared, right? So that's what we have right there. Okay, but then notice, what would tangent of theta be? Well, tangent theta is opposite over adjacent, so it's the square root of x squared minus 9 all over 3. Okay, and that's what I'm plugging in right there for tangent of theta. Okay, so that's our final answer. Now, this is actually a problem in the book, and I looked at the answer in the back of the book, and it said this. And I was like, why would they put this? Well, what they did was they rewrote this. Since both of these are over 3, they give a common denominator there. And then they used the quotient property of logarithms. So the absolute value of a quotient is the quotient of the absolute values. And then you could do natural log of the top minus natural log of the bottom. But the natural log of 3 is just a constant. And so you can kind of absorb that into the constant c. So that this constant technically is different than this one, but it's still just plus a constant on the end. So this answer is really equivalent to this answer here. But I'm totally fine if you just leave it here. It's just sometimes the back of the book simplifies things, sometimes in weird ways or farther than you would absolutely necessarily have to do it. Okay, let's do another example. Now this one, we have a 4 minus x squared. Okay, so our substitution is going to be with a sine. Okay, if it were x squared minus 4, it would be a secant. Okay, x equals 2 secant. Or if it were 4 plus x squared, or x squared plus 4, it'd be x equals 2 tangent theta. Okay, but it's x equals 2 sine theta here. Then dx would be 2 cosine theta d theta. Okay, so let's plug things in. Well, if we plug in the dx is the 2 cosine theta d theta, and the x is 2 sine theta, this is what we get. Okay, now 2 sine theta squared is the same thing as 4 sine squared theta. And then both of these terms here have a 4 in it, so we can factor it out. We read it as 4 times 1 minus sine squared theta. Okay, and then that's all to the 3/2 power. Now remember, 1 minus sine squared is cosine squared. And so we can write this as 4 to the 3/2 times cosine squared to the 3/2. Okay, that's what we've written here. 4 to the 3/2 times cosine squared to the 3/2. And we still have this 2 cosine theta d theta out there. Now, cosine squared to the 3/2 is really just cosine cubed. Okay, because if you square something, then take it to the 3/2, remember 2 times 3/2, right, is just 3. Okay, and then 4 to the 3/2 is 8, because you take the square root of 4, which is 2, and then you cube it, which would be 8. Okay, so notice what we have. We have a 2 and an 8. That can simplify there to be 1/4. We have a cosine over a cosine cubed. That's really 1 over cosine squared. Now, 1 over cosine squared is secant squared. Okay, because it's really 1 over cosine times 1 over cosine. But remember, 1 over cosine is secant. Right, so it's secant times secant, which is secant squared. And actually, it's easy to integrate secant, right? It's just tangent. Secant squared. It's just tangent. Right? The derivative of tangent is secant squared. So we have 1/4 tangent theta plus c. So the question is, what's tangent theta? Okay, well, according to this up here, our original substitution, sine theta should be x over 2. Okay, so drawing our triangle here. Let's see if I can move this over just a little bit here. Drawing our triangle, we see that opposite over hypotenuse should be x over 2. And then this leg of the triangle, according to the Pythagorean theorem, should be the square root of 4 minus x squared. Okay, so if sine theta was x over 2, what was tangent theta? Well, tangent theta is going to be opposite over adjacent. X over the square root of 4 minus x squared. Okay, that's tangent of theta. So that's what we're plugging in right here. To get from tangent theta to this, we've gone back to x's now. And your final answer should have x's, just like your original problem had x's. Okay? So again, that was a trig substitution. Okay, now what about something like this? Now each of these problems, I'm trying to illustrate something a little bit different with each of these problems. And so there's a couple new things about this problem. So we're not just doing the same thing over and over again here. We have the square root of 25 minus x squared dx. Our substitution is going to involve a sine. Okay, x equals 5 sine theta. So dx will be 5 cosine theta d theta. If we do our substitution, so we plug in the 5 sine theta for x there, and the 5 cosine theta d theta for dx, this is what we get. Now this square root is going to simplify to be 5 cosine theta. Okay, so remember, you could work it out as write this as 25 minus 25 sine squared, factor out the 25 and so forth, but it simplifies to be this. So what we have really is the integral of 25 cosine squared theta d theta. We can pull the 25 up front. Now, how do we integrate cosine squared? Well, remember, we did this last time. We used this identity that cosine squared is 1/2 times the quantity 1 plus cosine 2 theta. Okay, so let's plug that in here. Now, so we have 25 halves out front. The integral of 1 will be theta. So don't write x, it's theta, because we're doing an integral with respect to theta. That's why these d thetas and dx's, they're always important out here. So the integral of 1 is theta. The integral of cosine 2 theta is going to be positive 1/2 sine 2 theta. Okay, now the big question is going to be, what's sine of 2 theta? Because we're going to draw a triangle that's just going to have a theta in it. What's sine of 2 theta? How can we figure that out? Well, remember, sine 2 theta is 2 sine theta cosine theta. Right? Remember that trig identity. So we're going to rewrite sine 2 theta as 2 sine theta cosine theta. This 2 and the 1/2 will go away. So now if we distribute the 25 halves, we get 25 halves theta times 25 halves sine theta cosine theta plus c. Okay, now the question is, what's sine theta and what's cosine theta and what's theta? Okay, that's another one. So notice our original substitution was x equals 5 sine theta. So sine theta is x over 5. Okay, draw our triangle. Right, sine theta is opposite over hypotenuse. So this would be x and this would be 5. And we have the square root of 25 minus x squared right here. So notice, what's Well, sine theta is x over 5. By the way, we can plug that in right now, right? Sine theta here is x over 5. Okay, what's cosine theta? Well, cosine theta would be adjacent over hypotenuse. So that's the square root of 25 minus x squared over 5. That goes right here. That's our cosine theta. Now, the one thing left is, what about the theta? Okay, it'd be kind of nice if we had sine theta or tangent theta or cosine theta, secant theta. But what about just theta? What do we have? What do we do? Well, remember, sine of theta is x over 5. So theta, one way to think about theta is it's sine inverse of x over 5. Okay, or you could write it as cosine inverse of this. Okay, but the simplest way to do it is it's sine inverse of x over 5. That's what theta is. And there's no nice way to simplify that. Okay, so our final answer is this. Notice the 25 and the 5 and the 5. Those will cancel. But what we have is 25 halves sine inverse of x over 5 plus 1/2 x times the square root of 25 minus x squared plus c. And that's your final answer. So in this case, we do kind of have a trig type function in our final answer. So sometimes that happens because this theta was just theta. It wasn't like tangent theta or sine theta or something. Okay, and notice we had to use some trig identities, by the way, in this one. So that sine 2 theta was 2 sine theta cosine theta, and 1 for cosine squared, right, to do this integral here. In fact, again, this really emphasizes what we did in the last section. In the last section is where we learned how to integrate cosine squared, right, how to do that trig integral. Okay, remember, trig integrals are integrals like this. Trig substitutions are integrals like this first one here, where we're doing a substitution that involves trigonometry. Okay, now let's do one that involves tangent. Okay, so this one's pretty simple. X is just 1 tangent theta. Okay, this is just, or in other words, just tangent theta. So dx will be secant squared theta d theta. If we plug things in, we're going to get a tangent squared here. We'll get a tangent squared plus 1 underneath the square root there. And we get a secant squared theta d theta out there, because that's what the dx is. Now, it turns out that tangent squared plus 1 is secant squared, and the square root of secant squared is just secant. So notice what we get is we have a tangent squared there on the bottom. This secant will cancel one of those secants. So you just have a secant there and a tangent squared there. Now, how do we integrate secant over tangent squared? Okay, or 1 over tangent squared times secant. Well, it turns out for this one, the simplest way to do it is to change everything in terms of sines and cosines. Okay, so secant is 1 over cosine. Remember, tangent squared is really like sine over cosine squared, right? Because sine over cosine, that's tangent. Okay, and then 1 over that thing will be like the flip of that thing. So it's really cosine squared theta over sine squared theta. And then we still have this 1 over cosine out here. Now this cosine will cancel with one of those cosines up there. And we just have cosine theta over sine squared theta. Okay, and this one we can do with a u substitution, right? Let u be sine theta. Du will be cosine theta, d theta. So what we get is just the integral of 1 over u squared, right? It's sine squared, so it's 1 over u squared du. Okay, and how do we do that? Well, we rewrite 1 over u squared as u to the negative 2. And the integral of u to the negative 2 would be u to the negative 1 over negative 1, which is the same thing as negative 1 over u. Okay, so, and that's negative 1 over sine theta, right? Because that's what the u was. Okay, so notice we had to do a trig substitution, and then we did a u substitution. Okay, but we're back to minus 1 over sine theta. Now, what's sine theta? Well, our original substitution was x equals tangent theta, so tangent theta is just x, or x over 1 is a way to think about it. So tangent theta is opposite over adjacent, so we have x over 1, and the hypotenuse will be the square root of 1 plus x squared. And notice that's what we have in here in the original integrand. Okay, so the question is, though, not what's tangent theta, which is x over 1, but what's sine theta? That's what we're trying to find here. Sine theta is opposite over hypotenuse. Okay, so it's x over the square root of 1 plus x squared. Okay, so that's what we have here. Negative 1 over x over the square root of 1 plus x squared. Well, 1 over this fraction is like the reciprocal of that fraction, and so this is our final answer. And again, it's amazing, really, what this process involved. We went from x's to thetas, and then we went from thetas to u's, and then we went backwards. We went from u's back to thetas, and then thetas back to x's in the end, using trigonometry and u substitutions and everything all along the way. But our final answer is this. And you can check the answer again just by doing like the quotient rule and the chain rule and so forth, and simplifying it, and you should get this original integrand. Okay, again, it's an amazing technique, what we just did. Okay, now one more, and this is the last problem. This time we have not just like x squared minus 4 or x squared minus 25 or 36 or something. We have a 9x squared minus 4. So how do we deal with this? Well, there's a couple ways that we can do this. And what we're going to do is not try to do our substitution right away. There are some ways that you can maybe rewrite this as like 3x quantity squared and then do like a u-substitution, then do a trig substitution. But here's, I think, the easier way to do it. I would factor out the 9 here. Now you might think we can't factor out a 9 there because it's not like it's 18 or 27 or 36. It's just 4. Well, we can write this as 9 times x squared minus 4/9. Okay, notice if you distribute that 9, this just becomes 9x squared minus 4. Okay, and then we can write the square root of a product is equal to the product of the square root. So this is the square root of 9 times the square root of this. And the square root of 9, of course, is just 3. But now notice we have a square root of x squared minus an a squared. Okay, in this case, our a would be 2/3, right? It's the square root of this thing, right, which is 2/3. Okay, by the way, all these ones I've given you have been nice perfect squares or something. The numbers like 4 and 9 is 16. If you had like x squared minus 7, the a would just be the square root of 7. Okay, but in this case, the a is 2/3. Okay, because 2/3 squared is 4/9. Okay, so we let x equal 2/3 secant theta, because again, it's x squared minus the a squared. If it were a squared minus x squared, it'd be sine, and if there were a plus there, we'd use tangent. Okay, but we use secant. X equals 2/3 secant theta. Okay, so dx will be 2/3 secant theta tangent theta d theta. Okay, that's the derivative of this. Okay, so let's plug that dx in over here, and then plug in everything for the x's. So we have 2/3 secant theta plugged in for x here and also for x there. Okay, when we work things out, this becomes 4/9 secant squared theta. And this whole thing here is going to simplify down to 2/3 tangent theta. So you could write out all the steps if you want. But remember back at the beginning when you make the substitution x equals a secant theta, it always simplifies to be a tangent theta. And our a in this case is 2/3. Okay, but notice this 2/3 and that 2/3 will go away. This tangent and that tangent will go away. This secant and one of these secants will go away. So the only thing we're left with is a 1 over secant theta. Now this 4/9 down here in the denominator can come out front as a 9/4, okay, because it's down in the denominator. And then this, the 3 and the 9, or the 9 and the 3 can simplify to be 3 over 1. So this is really 3/4 times the integral of 1 over secant theta, but 1 over secant is just cosine. Okay, and the integral of cosine is easy, right? It's just sine. So we have 3/4 sine theta plus c. And again, we're not done because we have to go back to x's. So what do we have? Well, if we look at our substitution here, x equals 2/3 secant theta. What is secant theta? Well, you can multiply both sides by 3 and divide by 2. Secant theta is 3x over 2. Right? Multiply by 3, divide by 2. So if secant theta is hypotenuse over adjacent, we're going to put the 3x here and the 2 there. And then this side will be the square root of 3x quantity squared. So that's really 9x squared. Minus the 2 squared, so minus 4. And notice, by the way, again, this square root is what we had here in the original integral here. Okay, that tends to be the way. If you ended up with like 4 minus 9x squared, you know you did something wrong here. Okay, because it should look like, have that same form that the original one does. Okay, so notice, the question is though, we're at this point here, what's sine theta? Okay, we have secant theta is 3x over 2. Sine theta would be opposite over hypotenuse. The square root of 9x squared minus 4 over 3x. And we just plug that in here for sine theta. And now these 3's will go away, and our final answer looks like this. And again, I challenge you to try to take derivatives of these final answers. Try to check your answer here to see if, when you take the derivative of it and you simplify it down, do you get the original integral here? And you should. It's a little messy, and it'll test your algebra skills a little bit, but it'll work. So this is really an amazing technique, this trig substitution, to solve integrals, but they're integrals of a very specific type. So the thing that kind of ticks off something in your mind that maybe I could do a trig substitution is if you have one of these things like a square root of a squared minus x squared, or x squared minus a squared, or x squared plus a squared. And the substitutions that you're going to do are always going to be one of these 3. You'll never do like a cosine theta or a cosecant theta or something. It'll always either be a sine theta, a tangent theta, or a secant theta. And when you make the substitution, they'll always simplify to these things over here.